Right, let's look at now how concentration will affect this Maxwell-Boltzmann distribution curve. Now, when you increase concentration, you already know from theory that higher concentration means higher reaction rate, and that is because concentration just refers to how many particles are taking part in the reaction. So if you have a higher concentration, it just means you have more particles, and if you have more particles, it means more of those particles will have enough kinetic energy, and then they will collide with each other effectively, and then the reaction rate will increase. Now, if you are looking at the Maxwell-Boltzmann distribution curve, this is the bottom graph, which is marked as C1. This graph corresponds to the reaction with a normal concentration, so just the original concentration. And from here, can you see that again, this white part of the graph shows all of the molecules that don't have enough energy, so they will not be taking part in the reaction. And activation energy is this dotted line, so everything on the right of it, which is this blue shaded area, those are the molecules that do have enough energy and they will take part in the reaction. Now, if you increase concentration, it just means that you are adding more particles. So whatever number of molecules you had in the beginning, now you have even more particles. So can you see on the y-axis you have the fraction of molecules, which is like the amount of molecules. So when you increase concentration, now you will get a new graph, which is marked as C2. Can you see that this graph is much higher than C1? And that is because you have just increased the particles. So it will be at a higher value compared to C1. Now the whole entire graph is going to be higher than the original graph because now you're dealing with more molecules instead of less. And because of that, if you're looking at the shaded part, which is at the right of activation energy, this area now is much bigger than the original one. So it's going to be this green part and this blue part together, which means because you increase concentration, there is more particles, so more particles will have enough kinetic energy. So this is why the area under this curve is greater, which means more particles will take part in the reaction. Now, if you are looking at the difference between a change in temperature graph and a change in concentration graph, let's look at how you can differentiate between the two of them. Now, when you change in concentration, you are just increasing the number of particles. So the entire graph shifts upwards, or the whole graph itself is going to increase. So if you're looking at this original graph, it's lower. And if you're looking at a graph with increased concentration, it's much higher. So you're just increasing the amount of molecules, and nowhere in the graph can you see an intersection. This original graph and the new graph, they're not intersecting with each other because the whole thing is shifted higher because now you're dealing with a larger amount of molecules. But if you're looking at the change in temperature one, you're not changing the amount of molecules in the system. Whatever amount you had in the beginning, you will have that same amount afterwards. You are just making them all have more kinetic energy. So for a change in temperature, you're not shifting the graph upwards like concentration. You're shifting the graph to the right, because now the value for kinetic energy is increasing. So when you shift it to the right, the whole graph shifts to the right, which gives you a higher energy after activation energy. And because you're shifting it to the right and not upwards, you will have an intersection in this graph. So if you see a shift to the right, it means you're changing temperature. And if you see a shift upwards, it means you're changing concentration. Okay, now let's look at the third way which we can increase the rate of reaction, and that is by using a catalyst. Right, now a catalyst is just a substance that you use that speeds up a reaction, and the only way it does that is by decreasing activation energy of the reaction. Now we have done this countless of times, but just remember, activation energy is only decreased when you use a catalyst. That's all a catalyst does, decrease activation energy. And the important thing about catalysts is they only speed up the reaction. They don't take part in the reaction. They don't get used up in the reaction. They do nothing else besides speed it up by decreasing activation energy. So if you have a certain amount of a catalyst that you put into the reaction, at the end of the reaction you will have that same amount because it didn't get used up. So nothing happens to it, it just speeds it up. Now if you're looking at a potential energy diagram, and remember this is potential energy, not Maxwell-Boltzmann, okay? So if you're looking at this graph, the activation energy without the catalyst is the graph that is a solid red line, and that will be from the reactants to the highest part, which is the activated complex. So this distance here will give you activation energy. And if you're looking at the dotted line, this is now the graph when you used a catalyst. And the only difference between the graph with and without a catalyst is that the one with the catalyst is much shorter, which means that the distance from reactants to the highest point is much lower, which only tells you that a catalyst decreased activation energy. But everything else, reactants, products, change in H, everything else is exactly the same. Now, let us look at how a catalyst will affect the Maxwell-Boltzmann distribution curve. Now, here is the curve here, with and without the catalyst. Now, the thing to remember is when you're drawing a Maxwell-Boltzmann distribution curve, for a reaction that has a catalyst or does not have a catalyst, you don't need to draw an entirely new graph like how we did for temperature and concentration, because the catalyst only does one thing, which is change the activation energy. Now, let's look at this graph here. So again, it looks exactly the same. You have the graph, then you have this white part. This is all of the molecules that don't have enough energy, so they are not going to react. And then you have activation energy here, which is without a catalyst. And this part is the part corresponding to the blue shaded area. And now, when you do have a catalyst, can you see now the activation energy is shifted to the left, which is a lower value. So, because you used a catalyst now, activation energy just became lower. So, we don't actually have values here, but if it's to the left, it's a lower value. So, if you shifted it to the left, you now have increased the area under the graph, which means you increase the amount of molecules that take part in the reaction. So that is what a catalyst does. It just takes this activation energy, it makes it lower, so the graph shifts to the left, and now the area under the graph is greater, which means more molecules can take part in the reaction. So that's all you need to know. It just decreases activation energy. Now again, if we take this graph and we shift it or we flip it over, we're going to get it to look like this here. And if we compare it to the potential energy graph, with or without the catalyst, we will see that the activation energies of the reactions, it links up, or it basically corresponds to each other. So this purple graph here is showing the graph that is using a catalyst, and the activation energy of this graph, which is from reactants to activation energy, is corresponding to the activation energy on the Maxwell-Boltzmann curve that also uses a catalyst. And without the catalyst is this blue part of the graph, and it's also this red graph on the potential energy diagram. And whatever the activation energy is here, it's corresponding to the one here, which is without a catalyst. So that's just something nice to know. Okay, then we're just going to look more now at catalysts. Now you get two different types of catalysts. The one is homogeneous catalysis or catalyst, and the other one is heterogeneous catalysis. Now in grade 10 you done homogeneous and heterogeneous mixtures, and it kind of means the same thing here. Homogeneous is when you're dealing with things that are in the same phase, and when you add them together they just look like one solution. Right, so homogeneous catalysis is just when you have a catalyst and the reactants in the reaction are in the same phase as the catalyst. So for example, if you're using reactants that are liquids, then the catalyst can also be a liquid, and then they will form a solution and they will all look like one uniform solution. Right, then you get heterogeneous catalysis, and here hetero means different. So here the catalyst and the reactants will be in different phases. So maybe the reactant is going to be a liquid, and maybe the catalyst will be a solid, and it's not going to dissolve. So you will be able to see the different parts of the mixture. So it will be heterogeneous. Okay, don't worry too much about that, but just so you know. Right, and here are some examples of common catalysts that we use. Now, one catalyst that you use is vanadium pentoxide, which is V2O5. This is something that they use commonly when they make sulfuric acid, which is called the contact process. Right, and then you have iron or iron oxide, which is a catalyst they use when they're making ammonia in the Haber process. Then you also have nickel, which is used in the hydrogenation of carbon to carbon double bond. So if you remember in organic chemistry, when you want to add hydrogen to an alkene, you're going to use nickel. That can be one of the catalysts. Then you have sulfuric acid. This is very common, and this is what you should know also in making esters from an alcohol and carboxylic acid. Sulfuric acid is the catalyst. Another kind of catalyst you can use is also manganese oxide. That's to make hydrogen peroxide. Other common catalysts are also platinum, palladium, and rhodium. So if you see any of these in a reaction, just know it is the catalyst.